Hello, my name's Daryl Korn, and this is my walkthrough of Homework 1. Let's get into it, and we'll start with the code. This is my Python script for Homework 1. I've got some functions to import the iris data, and then I start with part A here, where we only use the first two features, and we're comparing three different distance metrics, and we're varying the k parameter from 1 to 11. So we got a loop for each metric, and then I've got a loop for all the k values. When I run it, I get a graph that compares all these metrics, like so, which I will explain in the PowerPoint. Oh, I guess we're running another part as well. So after part A, we have part B, we want to create a scatter plot of the best metric that we find in part A, which looks like so. Euclidean distance with k equals 4. That was our found best metric. Part C asks us to generate three plots that display the training data and assign different colors to the regions of the three classes. And that looks like so. Using that mg-learn package from the book. Then part D asks us to rerun part A, but we use all four of the features. So that'll generate a different looking line graph to compare the different k values across the three different metrics, like so. And then finally, we have part E, which compares our findings from part A and part D. And so I put that onto a single graph, which looks like this. And I explain all these in the presentation. So without further ado, let's get into the presentation. All right. For part A, we only wanted to compare the first two features to keep things simple, and that would be the sepal length and the sepal width within the iris data set. And then we compare three different distance metrics. So I use the Euclidean distance, Manhattan, and Chebyshev distances. And our k values range from 1 to 11. And my chart here in the top right, figure 2.1, shows my results. And you can see that at k equals 4, I achieved the highest accuracy for all three of my distance metrics, with the Euclidean achieving the very highest at 84.2%. When k was from 1 to 3, we see evidence of the model overfitting. It's too complex and it's not, it's making mistakes, not capturing everything that it could be capturing. Whereas when k is from 5 to 11, now the model is too simple and starting to underfit. So the best accuracy clearly is at k equals 4 and using Euclidean distance. So for part B, I dive into these best parameters a bit more. And I see what the model correctly classified and what it misclassified. I've got that scatter plot showing that here. The setosas are indicated as the circle shape. The versicolors are triangles, and the virginicas are the x's. So we can see that with these parameters, the model correctly classified all setosa examples. There are no red circles, but it did misclassify two versicolor samples and it misclassified three virginica samples. And the reason is because I've got an interesting one circled right here. It seems to be that virginicas and versicolors, they overlap quite a bit. And here we actually had a training bit of data that was in the same spot as a versicolor. So you can see why the model would have gotten that one wrong there. So on to part C. This is displaying all of our training data, but we try to split the backgrounds to show like the different areas of the three classes. And you can see when we keep k equal to 1, it's a bit choppy. Over here, it's showing that the model is overfit. Whereas when k is 4, this is the optimal distance, we can sort of surround all of or the most amount of samples and get the highest accuracy. Whereas when k is 11, now our model is too simple. And while the lines are very smooth and they look very neat, we misclassify quite a few samples there. So k equals 4 is a happy medium. All right. On to part D, and this is where we go back to A and we include all four features. So not only do we have the sepal length and the sepal width in the data set, we're also using the petal length and the petal width now. And I found that I was able to achieve much higher accuracy at 97.4%. Um, and that was across all three distance metrics, Euclidean, Manhattan, and Chebyshev. So it didn't really matter which metric you used at this point. Um, and while part A asked us to only use k values from 1 to 11, I found that you really had to move that k out pretty far to start getting the model to underfit. So I pushed it all the way out to 50, and I found that the model began to underfit around k equals 22, which is evident here in figure 6.1. And also, this figure shows that there's not much evidence of overfitting. I guess the problem is just rather simple. Um, but you do see a little bit of overfitting for the Manhattan and Chebyshev algorithms before k equals 10, just a slight bit. Whereas Euclidean doesn't have any overfitting at all. So we will now compare our results here in part E. So clearly, if you're going for accuracy, the best model to use would be Euclidean. It would use Euclidean distance. The k would be somewhere around 10, but you clearly have a big range to choose from. Up to 20 would do, really. And you would also want to include all four dimensions of your data because at 2 dimensions, the model, they're too close together, and the model is not able to draw a nice classifying line between the different classes. Whereas with 4 dimensions, it is able to separate out those classes much easier. So, yeah, if you're going for accuracy, using all 4 dimensions is optimal. There is one drawback to that, and that it is very difficult to visualize and maybe even interpret those results because you can't create a 4D figure. Whereas if you did only use the first 2 dimensions, it may be less accurate, the model, but it would be much easier to interpret in how it's operating in a 2 dimensional space. And there is something to be said for that. But 97.4% accuracy is pretty darn good. So it's nearly perfect. So I think including all 4 dimensions is the way to go, ultimately. All right. That sums up my homework 1 project. Thank you very much for listening.